Pick a whole number, any positive integer. When you subject that number to two simple rules, you generate a sequence of behavior so erratic that it has paralyzed mathematics for generations. If your number is even, divide it by 2. If it's odd, multiply it by 3 and add 1. These rules send the sequence into violent spikes and sudden crashes. It looks like white noise, bouncing across numerical scales with no apparent logic. But the mystery lies in the destination. No matter how large the starting value or how long the sequence rages, every trajectory eventually collapses into the exact same cycle: 4, then 2, then 1. This is the Collatz conjecture. Despite its simplicity, we possess no formal proof to explain why every path must return to that single origin point. The Collatz conjecture tracks the integer shadow of a continuous physical geometry, a recursive architecture that governs how systems manifest and resolve throughout the universe. We identify this architecture through the Dual Caustic Universe Framework, or DCU. This is a metastructure designed to bridge nonlinear dynamics and physical manifestation. The DCU operates on the principle that reality is not a linear march from a beginning to an end, but a bounded, recursive loop of action and reaction. Every cycle within this loop follows a 4-stage process: a primary split, a manifested traversal, a filtration of invariance, and a unified return. In the DCU topology, we denote this sequence as the 2-3-7 operator calculus. This structure is scale invariant. The same 2-3-7 rhythm that coordinates the pulse of a human heart also dictates the phase transitions of cosmic fields. The chaotic jumps of the Collatz sequence provide a discrete, frame-by-frame map of this exact architecture. We can translate the arithmetic of Collatz into geometric vectors of directional force. The rule to divide an even number by 2 serves as a contraction operator. It performs a binary constraint, stripping away excess magnitude. We call this the gravitropic vector. This downward force acts like gravity. It necessitates a reduction in the system's state space, forcing the sequence to ground itself and seek its origin. The rule to multiply an odd number by 3 and add 1 acts as a forcing term. It injects new structure and energy into the system. We call this the phototropic vector. This upward force drives the system further into manifestation, increasing its complexity and branching outward like a growing canopy. Every sequence we track is a real-time negotiation between these two physical vectors, an alternating pulse of expansion and compression. Collatz demonstrates how physical systems utilize this tension to move through a landscape of chaos toward a point of stability. These discrete arithmetic steps are low-resolution reflections of the continuous operators used in calculus. The contraction seen in the division step maps to the derivative operator. Within the DCU, we define this as the earth operator. Just as the derivative isolates an infinitesimal difference to define a rate of change, the earth operator differentiates continuity into measurable, terminable events. The expansion seen in the odd number rule maps to the integral operator. We define this as the water operator. While the derivative strips down, the integral accumulates. The water operator preserves memory and carries the system's total state across phase transitions. Between these two fields exists the tree, the active traversal buffer where the forces of differentiation and integration meet. The tree acts as the engine of the 2-3-2 loop, forcing the cutter of the derivative and the carrier of the integral to negotiate a stable path. In this model, the discrete steps of Collatz are the integer silhouette of this continuous, high-precision calculus. This creates a fundamental question. How does the system ensure this negotiation leads to a resolution rather than endless divergence? The resolution occurs at node 7. This is the coordinate where the initial split, the 2, meets the triadic formation, the 3. In calculus, this stability is maintained by the constant of integration, plus c. It functions as the system's memory, ensuring the initial conditions aren't lost as the state transforms. Node 7 represents the structural alignment of the fundamental theorem of calculus. The theorem proves that differentiation and integration are exact mathematical inverses. This inverse relationship means the earth operator and the water operator act as a single reversible engine. One splits the field,
the other restores it. We call this point of synchronized overlap the fruit state. At the fruit state, the accumulation of the integral and the manifestation of the derivative coincide. The fundamental theorem provides the formal proof that this interaction is lossless. It guarantees that the system's mathematical loop seals itself at node 7 without losing its essential information. We typically view closure as a point of termination, the end of a process. But at node 7, closure takes the form of a saddle node bifurcation. Part of the system follows the stable manifold, compressing downward toward Earth as the gravitropic return. Simultaneously, the unstable manifold launches upward. This is the seed for the next sequence. In this topology, the moment the cycle ends is the exact geometric coordinate where the new one begins. The compression of the fruit toward the ground releases the specific energy required to launch the next recursive loop. This bifurcation model scales from the integer lattice to the behavior of the observable universe. It challenges the assumption that the universe follows a linear path from a Big Bang toward a terminal state of heat death. If the laws of physics are dictated by this continuous calculus, the universe defaults to structural return, actively resisting terminal entropy. This is the finite to infinite principle. Bounded systems generate infinite complexity because their mathematical closure guarantees their continuous renewal. The convergence of every Collatz sequence to 1 serves as the integer signature of this topology, the proof that the universe operates as a perfectly conserved loop of return.